For the last couple of years, I've launched a good few rockets. Most of them were just simple Estes starter kits, until I built Falcon Bobby. This was the first ever rocket I made from scratch, and it was a pain to get right. It took 2 failed launches and many changes, iterations and tests to finally get it straight. I learned a lot when building it, and now I thought I was ready to make something even bigger. I think. I was a bit overly confident when I made the decision. Falcon Bobby 2.0. The name may not have taken much effort to make, but the rocket itself certainly did. This rocket stands nearly 60 centimeters in height. It's even too high for it to be fully in shot. I'm probably going to move it down in a second. It's 7 centimeters in diameter, and it was a bloody nightmare to build. This is also going to be the first rocket that I make that uses a cluster of motors. If I just very carefully tip it over, you will see 3 motors is going to be used on this rocket. This is basically going to make it 3 times as powerful as Falcon Bobby 1.0. This video will be covering the whole designing, building and testing process of this new rocket, and there will be a separate video coming out hopefully in a few days time after you're seeing this that will actually cover the first maiden launch of this rocket. I'll leave timestamps in the video's description so that you can skip and go to whatever parts that you find more interesting, but without further ado, let's get started. I'm gonna move this over down to here. So, let's start with the motors. Falcon Bobby will use 3 D12-3 Estes motors. If you don't know what these letters and numbers mean, I'll summarize it quickly. The D at the start symbolizes the power rating of the motor, so basically the size and the amount of black powder inside. They run in alphabetical order, so for example, a D motor is twice as powerful as a C motor, and so on. The number after that, the 12 for this motor, symbolizes the average thrust force, so basically how fast the propellant inside the motor burns. Let's take 2 random motors as an example, the B4-4 motor and the B6-4 motor. These 2 engines will get the rocket to roughly the same altitude because of their power rating being the same. The only difference between these 2 motors is the burn rate. The B4-4 motor will burn a bit slower than the B6-4 motor. The final number is pretty simple. It symbolizes the delay in seconds between engine burnout and the injection charge, which fires the parachute. The motor we're using, the D12-3 motor, will have a 3-second delay between when the engine runs out of propellant and the parachute is deployed. After all that, hopefully you can now tell that this rocket is going to be a lot more powerful than all my previous rockets, and it's going to use 3 of these motors. This amount of thrust will be needed, however, as the whole rocket weighs about 1 kg. And in model rocket terms, that's actually pretty heavy. Holding a motor like this in place was a challenge when making the first Falcon Bobby. Before its 3rd flight, I had to completely redesign the motor case to make sure it would be secure inside. I had to order specially made O-rings and tubes to make sure that the motor wouldn't be an issue. I knew that in order to hold 3 of these motors inside a rocket twice the size, I was going to need to do something similar, which is why I decided to get the motor case 3D printed. This had many advantages. I could design it completely by myself to make sure everything would be in the correct shape and sizes that I needed for this very specific part. The disadvantage was that I had to design it myself, which I didn't really know how to do. In order to actually make something out of basically nothing, you had to design it first in a 3D printing software. For this, I used a software called Onshape, and before I actually got to designing the motor case itself, I decided to try, as accurately as possible, to design the Falcon Bobby 2.0 rocket as a whole in the software, to get some practice. So I guess the best place to start would be trying to make the cylinder of the main body. So how do I do that? If I sketch. Alright, okay. Then we want to draw a circle. So how do I do that? Ah, here we go. Diameter is 7 centimeters. So if I go... Actually, I need to get my units. I don't know if this is even in centimeters. I hope it is. Yes, it's in centimeters. That's good. Alright, diameter is 7 centimeters. I'm going to make that kind of exact. Right, so now we have a circle on the top plane. We can use this to actually make a cylinder, I hope. So if I use the extrude feature, will that work? Oh, okay, yeah, I did something. It needs to be more the depth. Needs to be 29 centimeters. There we go. Okay, right. That looks about right. Now we've got a cylinder, and now we should be able to... I need to make it thick. Like, I need to make it 0.7 centimeters thick. A shell, that's what I use. It's red, so that can't be good.
The shell feature allows you to remove material from...
Yes, that's what I was looking for. Okay, now we're getting somewhere. What's next? We need to make the nose cone. So if I could create a new plane.
The loft feature allows you to transition between sketch profiles.
I'm going to click on my face of my circle and the point.
Oh.
Point becomes a point on the circumference of the circle.
0.5, and I'm going to click over here.
Okay, that does not look that good. I've been recording for about an hour. This is this is what I've been able to come up with.
By default, offset the plane from a planar.
Okay, that's a bit better. If it wasn't a different color, it wouldn't pop out as much. Can I change the color? So that's kind of the nose cone done. I mean, I hope anyway. I think it is. Now it's just on to the fins. So where do I start? We gotta get sketch. Oh, hold on. I've made the actual body too small. Give me a second. That's more like it. Okay. Only thing is though, we do need to make it 3D. Right now it's literally just a 2D sketch. And this is a bit tricky because I'm not sure how to do that. There we go. Now we've made it 3D. That was easier than I I thought it would be. Okay, now we just have to do that for 3 more times around the sides.
In this video, I'm going to demonstrate how to actually copy and paste objects.
Alright, well, there you go. It does look a bit weird. I think the fins are a bit too big, but it's cool to get at least a little visualization of the rocket before you actually build it yourself. This is kind of a very basic sketch. Obviously, there's nothing inside it, there's nothing in the nose cone, it's just a kind of a mock-up. I probably will make the fins a bit smaller because they do look quite massive and stupid, but I'm not sure if there's anything else really to add for this. Considering it was my first time doing anything in Onshape, I think it was pretty alright. After the very tedious process of trying to make that bloody stubby ass nose cone in the 3D software, I mean, look at it. Like, this is what that's what it's shaped. It's not a perfect cone. It's like not pointed, it's rounded. I couldn't for the life of me figure out how to do that. So if there's anyone who uses Onshape in the comments, please let me know. The design for the motor case would be pretty simple. I started out by drawing 3 cluster-shaped tubes that would hold the motors. These tubes would then be surrounded by 2 O-rings that would fit nice and cozily into the main rocket body. I then extruded the whole thing, not without some issues, added a forward closure, and done. A fully functional motor case. Well, not yet. I sent my perfect design to a company called Werg that will print your models for you, because I didn't have a 3D print myself, and ordered a quote for my model. A week later, this arrived on my doorstep, a seemingly empty box. This raised some concern and I contacted Werg. It was only after I contacted them, however, that I realized that there was actually something in the box. It was a small plastic bag containing my 3D model, although a much smaller version of it. I was pretty confused and told them about it. Their response suggested that when I exported my model from Onshape, it didn't save as a 1:1 scale, so basically instead of exporting the model in centimeters, it came out in millimeters for some reason. I made sure that all the dimensions were correct before sending it to them, so I had no idea why it just converted the units. Regardless, I had some redesigning to do before I could get it printed again. So I did what I probably should have done in the first place, seeing as I don't know much about 3D printing at all, and I sent my design over to an expert to review it and see if it would actually be able to print properly before actually getting it to print. They got back to me and suggested some design changes to be made. I did those changes and came across the reason for the dimension problem. For some reason, even if I exported the model in centimeters, it would always come out in millimeters, no matter what. I told them this and asked if they could resize the model themselves to the correct dimensions before printing. Thankfully, they did just that and sent me a proper model in centimeters. Finally, I sent that model to get 3D printed, and finally, a couple of days later, this arrived on my doorstep. I then slotted it into the main rocket body tube, and there was a bit of sanding that needs to be done, but otherwise it fit perfectly. I bought some Gorilla epoxy.
Oh, you finally fixed the chair.
You know it. Whoa!
And secured the motor case firmly and securely inside the main rocket tube. Unfortunately, I wasn't going to be able to do a static fire on this test. Usually, in the case of Falcon Bobby 1.0, I would do a static fire test in between flights to make sure everything would work properly. It would be able to make sure that the motor wouldn't fly off or the parachute wouldn't just also fly off. However, because this rocket was so big and had to use 3 motors, and said motors are also very expensive, I wasn't really able to afford to waste, not necessarily waste, but use up 3 motors just to not even fly it properly. So that meant I really had no idea whether this thing would actually work, or whether the parachute will fully deploy properly, or even the 3D printed motor case would even hold the motors in place. So for the rest of this design process, we're basically going to be winging it and hoping for the best. Next up, the recovery system, aka the parachute. The parachute is not the only thing that is used to get the rocket safely to the ground after launching it. There's also more equally important parts to it. The shock cord of a rocket is basically a very strong rope or elastic that's used to attach the parachute and the nose cone to the rest of the body at deployment. How most model rockets work is that when the motors burn off all of their fuel, there's a bit of a delay in between when the motor burns out and the parachute deploys. There's a bit of an explosive charge on the top of the rocket that shoots out a bunch of energy that pops the parachute out. The energy created from this is enough to actually get the parachute out of the rocket far enough so that it can actually deploy. However, if you don't have a strong enough shock cord, the parachute along with everything with it can just completely detach from the rocket. This is actually something that happened on Falcon Bobby 1.0. Instead of using a strong enough rope or elastic, we just use a normal rope. The rope that the parachute was attached onto along with the nose cone flew off and got yeeted out the top of the rocket. To avoid this happening again with Falcon Bobby 2.0, I was thinking of using a nylon or Kevlar rope. Kevlar is very, very strong, and if you don't already know, it's the same material that's used to hold up bridges or make bulletproof vests. It's probably a bit overkill, and that's why I didn't really want to use it, and it's also very expensive. Nylon, on the other hand, was less expensive and a bit less strong, but I couldn't find it anywhere. So instead, I decided to use a sort of elastic rope that I found in a random hardware store. I'm not entirely sure what it was made out of, but it was elastic, so it would have been able to absorb most of the shock anyway. I bought a couple of these and then realized that they had little hooks on the end of them, so I had to cut them off. Maybe I could use them for something else in the future. I attached the shock cord to the inside of the main rocket tube, and I also tied a little knot on the top for the parachute to be able to hook onto. Next, I attached the nose cone to the top of the shock cord. I did have some concerns as to whether this whole thing would be able to, hold up against all of the pressures from the motors. But since we couldn't do a static fire test, I guess we're just gonna have to wait and see. I don't want the whole shock cord to come apart because that actually happened to one of my previous rockets.
Oh wow, that's bad. That's bad.
It would be pretty funny if that happens, but also a lot more dangerous considering this thing weighs twice as much and is twice the size. Anyway, next up is the parachute itself. There are many materials you can use to make a decent chute. It mostly depends on the size of your rocket and how high it's going. My rocket is pretty big, but it's not actually going to go that high, so it needs something in between. For low power model rockets, like a few of my previous ones, you can use just like simple plastic or something, and a lot of them just already come with it. But for larger, more powerful rockets like mine, or even more powerful, you're gonna have to use something like nylon. It's a bit more expensive, but it's a lot stronger and can sustain a lot of load. Remember, the parachute is gonna be basically slowing down the whole rocket as it comes down, and it's gonna be under a lot of force. So where was I gonna get enough nylon to make a decently sized parachute? I did my calculations and figured out that for the weight of this rocket, it's gonna need about a meter wide parachute to give it a slow enough descent rate after parachute deployment. You kinda have to strike a balance in between how long you want your rocket to stay in the air for and how fast you want it to hit the ground. Obviously, the main purpose of a parachute is to slow the rocket down enough so that it can be recovered in one piece. But you don't want it to be in the air for too long, because then it will drift really far away and get taken by the wind. But then again, you don't want it to be just like burning down in the freefall. For the first Falcon Bobby, I used a bit of umbrella for the parachute. I only cut out about a 9-inch wide parachute, and that definitely wasn't enough. So I was going to use the same thing, an umbrella, but this time I was going to use the whole umbrella. So I bought the new umbrella, stripped off the fabric. I added some pieces of duct tape around the edges where the strings would attach onto. I saw that from a handy video, I can't remember the name, but I'll put it in the description. The duct tape will basically reinforce where the attachment points are and stop it from ripping too much. You can have a very, very strong rope, but if the attachment points aren't strong as well, you're gonna have a bad flight. I bought some smaller strings made out of plastic and attached them to the parachute. And now we have a fully functional parachute, nearly. I attached it onto the shock cords using the little knots that I made earlier. There's only two major things that I'm worried about for this recovery system. Number one is that the shock cords might not be long enough, and number two, I'm not 100% sure if the Gorilla epoxy is going to be strong enough to keep everything attached. But guess what? We can't do any tests really until it's in the air, so we're gonna have a pretty unpredictable launch in a few weeks' time. Almost everything was now done on the rocket apart from the actual fins. Before we continued on the main rocket itself, there was something I wanted to test that I found quite interesting. Another thing I was quite worried about for this rocket was not getting all three of the motors to light simultaneously. The launch controller that I was using previously was kind of weak, and it was only really able to launch one motor at a time. Each motor requires its own set of voltage to be able to actually light up reliably, and that launch controller just didn't really have enough juice in it. So I bought this, the Estes Pro Series 2 controller. It came equipped with 2 sets of alligator clips instead of just one, and uses 6 C-cell alkaline batteries for 9 volts of power. This launch controller was actually made to be able to launch multiple motors. However, I was still pretty worried that this wouldn't be enough. You see, the actual Estes igniters, which are the things that you attach the little alligator clips to and then you stick it into the motor to light it, they aren't the most reliable. Literally, if you leave them out in the air for too long, they can just stop working because of the humidity or something. That's what I had to deal with when I was trying to launch some of my other rockets. However, I found something that you can actually use to improve the kind of fiery aspects of these igniters. There's a chemical called nitrocellulose, whatever. It's a highly flammable compound found in many things such as lacquer or nail polish. So I stole some of my mom's spare nail polish and dipped one of my igniters into it. I did want to test to see if this would actually improve the burn rate at all, so I got one igniter that didn't have any nail polish on it and another that did. I put them out side by side to ignite them at the same time and see if there was any difference. The results were okay. I was kind of expecting something a bit more. Right off the bat, you can see that the plain igniter lights first, followed shortly after by the nail polish one. Once the nail polish igniter lights up though, it fires up nicely. No sparks or pops or anything like that, but it was still a bigger flame than the plain igniter. The nail polish igniter also seems to burn faster. What does this mean exactly? I'm not really sure. I'm still not 100% sure if this change is worth it for the added risk of it maybe, you know, not working at all. So I decided to go one step further and actually try and ignite one of the motors to see if it actually ignites a motor. I had a spare D motor lying around that was just waiting to be lit. And it worked, so the nail polish one is actually able to light up a motor potentially more reliably than a normal Estes igniter. So for the launch, I guess we are going to go with a nail polish dipped igniter. Hopefully this would allow for all 3 engines to light up at the same time. I really do not want this rocket to fail just because one motor decided I'm not gonna light up. Next up is the launch pad. This rocket, as mentioned many times, is a lot heavier than my previous rockets, and so the launch pad that I was using previously probably is not going to suffice. Even with Falcon Bobby, I could see the metal launch rod, which is the thing you have to slide your rocket onto to keep it upright, was bending a bit under its weight. It was not going to be able to support this massive thing. I couldn't find any decent launch pads online that would suffice, so I decided to build my own. Something that's used a lot for launch pads for heavier rockets is something called T-slot rail. It's this funky looking piece of metal that you can slide things onto very easily. There's these things you could buy online as well called rail buttons that you could stick onto the side of your rocket and it would slide down into the T-slot rail very easily. However, no matter where I looked, I could not find it anywhere in person or online. Not the right sizes or for a decent price. As this project went on, it kind of became a more of a how can I save as much money as possible kind of project, because everything leading up to now has been quite expensive, especially the 3D printed motor case. So I decided to take the design of the other launch pad, the smaller one, and kind of just upscale it. I bought a much longer and thicker rod that I could use to slide the rocket down onto. I used some plywood that I already had lying around for the base of the pad, and I used a brick of wood to attach the rod onto the plywood. I forgot to mention this, by the way, but we also used shelf brackets to stick the piece of wood onto the plywood, and the rod did kind of bend a little bit, but it was acceptable. To actually allow the rocket to slide along the rod, I bought these things called screw eyes. I sawed off the excess and attached them onto the main rocket tube. The very tedious and frustrating process was trying to get them all to be very straight and align properly, and it was not the easiest task in the world, but eventually we got it pretty well sorted out. And now the final major thing to do on the rocket was to actually glue the fins on. I already cut out the shape of the fins that I wanted, and tried to just simply glue them on like I had with the first Falcon Bobby. The only problem was that these fins are a lot bigger, and they kind of tend to fall over. I had multiple failed attempts of just trying to get them to stick on straight, and trying to actually get them straight was also very difficult. No matter what, they would just keep falling off, and I had to think of something. By the way, not really a side rant, but a rant nonetheless. Putting fins on a rocket is the worst part of building a rocket. Next time, I'm definitely going to make a design that you could just slot the fins into the actual rocket and not just onto it. The main problem was the fins were kind of just falling off when they were drying. I had come up with a solution, however. All I did was glue a strip of paper onto the bottom of the fins, and that gave the fins a pretty solid kind of base to stay upright while it was drying, and it worked. We now had a rocket that actually looked like a rocket, and that's where we are right now as of recording this video. The rocket is basically ready to be done. I mean, there's still a bit of painting to be done, but don't worry about that. I'm very proud at how it turned out. To be honest, halfway through this project, I wasn't even sure if it was even gonna happen. I definitely kind of glossed over a lot of the nitty-gritty bits of this rocket just because I'm not sure if anyone would be interested in that. It's certainly not perfect. I mean, if you like really look at it, it's quite messy and, you know, definitely not the best, but for something this size, for me, you know, the limited resources I had, I think it's a pretty good job. As of recording this, we're just right now looking for a place to actually launch it, and once we find that out, we will hopefully be flying it in a couple of weeks. I don't know. By the time you're actually watching this video, it may have already even launched, so make sure you go follow me on Instagram. There's going to be more frequent updates and pictures and stuff like that on there. Hopefully a launch video will come out soon after this video, whenever we actually launch it. So please do go ahead and subscribe if you're not already, and because you don't want to miss out on that. Trust me, this launch is going to be exciting. Excitement guaranteed, whether or not it works. Thank you so much for watching this video, and if you did enjoy, please do give us a like. It would be greatly appreciated, and I will see you in the next video. Hopefully it will be about this rocket successfully lifting off and nothing goes wrong. Goodbye.